All right, so this is the first lesson from chapter 5, in which we're looking at relationships, specifically linear relationships, which is something that we've really dealt with in previous courses before. I'll just kind of build upon these ideas. And so first, here's a couple, some vocabulary here that may sound familiar or may feel new. First, what is a linear relationship? A linear relationship is one in which there's some sort of change, but the change is constant, which means whatever is happening, it doesn't speed up or it doesn't slow down. So if something's increasing, it's increasing at the same rate constantly. If something is decreasing, it's decreasing by the same value constantly. And when you graph, if you visualize the change of a linear relationship through a graph, the graph always forms a straight line. There's no changes in direction of the line or whatnot. That said, in general, there's two types of relationships, either continuous or discrete. This is a little bit harder to explain through a definition, but I'll do my best. If something is continuous, if your data is continuous, if your relationship is continuous, then the values in your data, the values in a relationship, can be infinitely divided, which means there's an infinite number of quantities between any 2 points. Or that you can whatever your quantities are, they have meaning to any number of decimal places. Like I said, it's tough to explain just through a definition. But in general, some examples are like, anything involving, or usually involving time. For example, if you have a value of something after 1 second and then another value after 2 seconds, in between those 1 second and 2 seconds, at 1.5 or 1 3/4 and 1 point whatever, that makes sense. A time of 1.8216 seconds makes sense. No matter how many decimals I express between between 1 and 2 seconds, for example, that value has meaning. Time isn't discrete. Time is continuous. And, I can break down a unit of time into any number of decimals I want. Similarly for speed or for the distance you traveled. These are all examples of continuous data. All right? Now, again, I'm not expecting that to be fully clear just yet. Like so many things, it makes a lot more sense when we start working with these examples. But the sort of contrast to that is discrete data, and these cannot be infinitely divided. There's a finite, which means not infinite. There's a set number of quantities, and they don't make sense between points necessarily. So, for example, number of people. Okay, if we're looking at the number of people as being part of a set of data, then this is discrete data, because 1 person makes sense, 2 people make sense, but 1.5 people does not make sense. 1.812 people does not make sense. The number of people is discrete. And notice it's very different from time. 1.92 seconds, that makes sense, but 1.92 people does not make sense. And it's all about the context of the data. Number of days, again, 1 day, 2 days, but 2.8 days could make sense depending on the context, but it also may not make sense depending on the context as well. It depends what the context is. But number of objects, if you're talking about counting number of chairs in a room, 1, 2, 3, 4, 5, 6 makes sense, but most likely 1.92 doesn't make sense. And so in general, discrete data, you can count it and you can list it out. Continuous, you cannot, because it's not something you can really count. That's it. I'm not saying again, this makes it completely clear, but hopefully it gets more clear as we work with different relationships and we discuss if it's discrete or continuous. All right, so with that said, here's a relationship. And the relationship between time and distance. And so this is meant to show the distance on a bicycle's odometer. An odometer measures the total distance that someone has traveled. And so this is showing the distance on a bicycle's odometer over the course of 7 minutes. So you can see time in the top row and distance in the bottom row. So my first question is the relationship between time and distance linear? So let's remember what linear means again. Linear means the change is constant. It doesn't speed up or slow down. So it's hard to tell just yet by looking at this table, but let's look for the change. And a natural thing to look at is what is the change from, in this case, 1 minute to the next? Well, from 4.5 to 5.2, we go up by 0.7 kilometers. And from 1 minute to 2 minutes, we go up 0.7. And if I keep checking, the change is always the same. For this particular relationship, every time we go from 1 minute to the next, we are going up by 0.7 kilometers. And so because this change, 0.7, is always the same, that means the change is constant, which means this is linear. Which means this person, over these 7 minutes, is cycling at a constant speed. If even one of those was not the same, if even one of those was 0.68, this would no longer be linear. It would be linear-ish, it would be very close to being linear, but it would not be exactly linear. But how convenient, this is exactly linear. So now, is this data an example of continuous or discrete data? And it's all about understanding the context. So looking at time and distance. And so one way, if you're not sure, is thinking, would it make sense to break this up to, let's say, 1.5? Would it make sense to determine the distance after 1.5 minutes? Yeah, that would make total sense. What about 1.1 minutes? Yeah, you could understand that makes sense, finding the distance after 1.1 minutes. And so this is continuous data. The change in time, the change in distance is continuous. Any value, even though we just have a table with whole numbers for time, any value in between, if I think about 0.1625 minutes, that makes sense, just a tiny bit more than 3 minutes. And so in the context, any value between these makes sense, so this is continuous. And so now, what is an equation that relates distance to time? And then use this equation to predict the odometer reading after 20 minutes. So I've already seen this pattern. We've already seen this linear pattern that we're going up by 0.7 every time. So how can I express this pattern, though? How can I express this relationship, but specifically talking about the connection between distance and time? To do this, we have to kind of look this way. We have to think when time is 0, distance is 4.5. When time is 1, distance is 5.2. When time is 2, distance is 5.9, and so on. And can we, looking this way, see the relationship? Can we see the connection, the pattern between the time and the distance below it? That's harder, but it does relate to this 0.7 we see looking this way. And so the key to this is realizing that we started off at 4.5 kilometers, which means the odometer was at 4.5 at the start of this ride. And so that 4.5 was there automatically. And then after that, every minute, we added 0.7. And once we realize that's what's happening, we start at 4.5, which means before we recorded this data, the person had already cycled 4.5 kilometers at some point in the past. But we started at 4.5, and then after that, every minute, we add an extra 0.7 repeatedly. And repeatedly adding something is the same as multiplying, right? For example, to get to 5 minutes, one way of thinking about it is we start at 4.5 and we add 0.7 1, 2, 3, 4, 5 times. So one way of getting to the distance at 5 minutes is to take our starting amount and add our change 5 times. And I could do that for any minutes. If I want to look at 3 minutes, I could take my starting amount, 4.5, and add the change, 0.7, 3 times. And so in general, if I want to look at just any number of minutes, I want to take my starting point, 4.5, and add the change, 0.7, x times, t times, whatever variable we want to use. And so an equation we could say is that d for distance is the same as 4.5, that was the constant, that's our starting point, plus this 0.7 times the number of minutes, and I'll put t for the number of minutes. And so that 0.7 that we found, that constant change from one to the next, was really important, but also was the starting amount, 4.5. And now I've expressed this pattern here of this table, this linear relationship I've expressed as an equation. D equals 4.5 plus 0.7t. And now once I have that, I can quickly use this to predict the odometer reading 20 minutes after riding, which means when t is 20. And so that means the distance will be 4.5 plus 0.7 times 20. And at this point, I can just go to a calculator and type 4.5 plus 0.7 times 20. And basically, if this person keeps riding at this speed, after 20 minutes, the odometer will show 18.5 kilometers. Now again, this is what we call extrapolating. I'm going 20 minutes is beyond the table. So it's a prediction, and it's based on the idea that this person continues to cycle at this constant rate. But if they do, this prediction will be extremely accurate. Obviously, if they just give up and take a nap, this prediction will not be so good. All right. So with that said, we'll look more into this in the next lesson, which is also from the same section of the textbook.